You sick of all the same dudes running up.
Hello students and welcome back to my YouTube channel. This is Kashima Soni and today we are going to start a new chapter in the series of organic chemistry, that is proton magnetic resonance spectroscopy, that is H1 NMR. So we are going to see that how using NMR one can easily structurally elucidate a given sample and what is the exact structure of that given sample in a compound. So that is what we are going to see, that no, using UV and IR you cannot say that this particular sample has this structure. You cannot say that. You need NMR for that. So how NMR is going to help us in that case, that is what we are going to see in this particular chapter. So taking up the introduction portion, first of all, we are going to see that what NMR spectroscopy actually does. So NMR spectroscopy, as the name says, nuclear magnetic resonance spectroscopy, is definitely going to involve the nuclei of the atom that is particularly present in a sample. So in any compound, if we are going to talk about NMR, we are going to use the nuclei. Actually not nuclei, we are going to irradiate the sample under consideration with radio waves. And what will happen? Once the frequency of sample matches with the natural frequency of radio waves, what will happen? Absorption occurs, that means resonance occurs, and then this will lead to absorption, and ultimately the nuclei which has absorbed the radio wave frequency will change its spin from this to this. That means going to the higher energy state, it will change its nuclear spin. So that is what is going to happen in this particular complete NMR technique. Understood? So using this technique, what happens? It is used to determine the type, number and relative position of any certain atom in a molecule. So for example, let's just say कि आपके पास CH3, CH2, Cl है. तो अब आपको नहीं पता कि Cl आपका CH2 के साथ लगा है या उसके साथ फर्दर कोई और यहाँ पे आगे किसी और मॉलिक्यूल आपके एटम के साथ ही अटैच्ड है. You don't know that. For that you need NMR. So आपका एग्जैक्ट पोजीशन यही है कि CH2 आपके Cl के साथ लगा है और CH2 के साथ आगे CH3 लगा है. इसकी कंफर्मेशन आपको NMR से मिलती है. इसकी पोजीशन की कि कौन सा सर्टेन एटम एक मॉलिक्यूल में कहाँ प्रेजेंट है उसके बारे में NMR से पता लगता है. ठीक है. And it is originally discovered by Felix Bloch and Edward Purcell in the year 1946, and both of them shared the Nobel Prize in Physics in the year 1952 for their pioneering work. And it has also seen a significant increase in the popularity with the development of FT-NMR spectrometers, that is Fourier transformer NMR. So what happened is that we are going to take up this particular instrumentation technique in the portion of instrumentation, where we will be discussing the instrumentation portion only, and in this chapter we will be focusing on CW-NMR and FT-NMR only, that is continuous wave and Fourier transformer. So in case any university and any college student is watching this video and you have these two topics in your syllabus, then let me tell you, this is quite important. And in the instrumentation portion, the examiner, you can expect that the examiner will ask you either continuous wave NMR or FT NMR. They might ask you the working and principle of these two instrumentation techniques of NMR. So don't worry about that. We are definitely going to take up that in this particular chapter series. So proceeding further, as I have already told you that what is NMR, it stands for nuclear magnetic resonance. It is quite powerful and analytic technique used to determine the molecular structure of chemicals. Now, as I've told you that it works by examining the response of certain atomic nuclei in the sample to strong magnetic field and radio waves. जो आपका sample under consideration है, आप उसको strong magnetic field उसके introduce करवाओगे उसके ऊपर, as well as आप उसके ऊपर radio wave insert करवा रहे हो. तो जो nuclei under consideration है वो क्या करेगा? Once the resonance occurs, absorption होगी radio waves की, तो क्या होगा? वो अपना spin change कर देगा on going from lower energy state to higher state. That is what is going to happen. So different type of atomic nuclei have different response. So ultimately हर nuclei अगर same response बताएगा तो आप कैसे differentiate कर पाओगे? So that is one thing ना. So different type of nuclei is definitely going to show different response to magnetic field and radio waves. So thereby analyzing the responses, scientists can easily determine the chemical structure of the sample under consideration. So it looks at the behavior of the spinning proton. So आपका जो proton यहाँ पे जो आपका ground state में present है, that is also spinning around its own axis, you know, just like the spinning top. That we will come to that particular topic also. So ये जो आपका ground state में भी जो आपका nuclei hai, that is also spinning around its own axis, just like your electron you know, revolves around its own axis. So that is one thing about it only. So it looks at the behavior of spinning proton in the molecule when placed in the strong magnetic field. Now, each proton in a molecule has a unique magnetic response, thereby allowing the NMR to distinguish between different chemical environments. तो अगर आपके पास ये example है CH3, CH2, Cl, तो ये आपका अलग response दिखाएगा, ये अलग response बताएगा, और उसके according आपके पास जो है आप बता पाओगे कि हाँ आपके sample में जो भी प्रोटोन है CH2 मिथाइलिन प्रोटोन या मिथाइल प्रोटोन है वो इस पर्टिकुलर जगह पे प्रेजेंट है, वो आप इसके थ्रू बता सकते हो. अब इसके लिए भी आगे बहुत सी चीजें हैं, आप आगे जाके केमिकल शिफ्ट पढ़ोगे, आप फैक्टर्स इन्फ्लुएंसिंग केमिकल शिफ्ट पढ़ोगे, उसके बाद बेसिकली आप कह सकते हो दैट यू आर वेल वर्स्ड इन दिस चैप्टर एंड देयरफॉर यू कैन इजीली गो ऑन डिटेक्टिंग और यू नो स्ट्रक्चरली इल्यूसिडेटिंग द गिवन सैंपल इन अ कंपाउंड. सो by analyzing the pattern of signals, peaks, in NMR spectrum one can easily identify the type and number of atoms in a molecule as well as their rearrangement. So, if we'll take the example of, you know, linear chain and branched chain compound. So, NMR is quite useful in, you know, differentiating between these two. So, that is one thing about it, and as I have already told you that it will give different kind of spectrum for linear chain and different kind of spectrum for this particular branch chain compound. Though they might contain the same molecular formula, let's just say that as of now they have C4H8. So they might contain the same molecular formula, but they are definitely going to give the different structures, and ultimately if they are going to giving the different structure, they are going to give the different responses in the NMR spectrum as well, right? So that is one thing about it, and therefore it is quite useful tool in chemistry, allowing the scientists to study the complete molecular structure of compound and also gain important insights into their properties as well as behavior. So that is about the introduction portion of this particular topic NMR. Alright, so the very next topic that we are going to take into consideration is your physical basis of NMR spectroscopy, that is nuclear spin. So try to understand this thing that as I have already told you, the nuclei, the sample under consideration will have many nuclei, many proton nuclei. They all are in the ground state are also spinning around their own axis. Correct? So, हर atomic nuclei की एक property है जिसको आप बोलते हो spin. Right? As if the nuclei behave as if they are consistently spinning around their axis. So, जितने भी magnetic nuclei होंगे, that is जिनकी I value is not equal to 0, will behave as a tiny bar magnet. Now the question arises, what is I? So, I over here is nuclear spin quantum number, just like your electron. जैसे electron के केस में आप पढ़ते हो, बहुत सारे electrons के केस में अपना spin quantum number, then आपका angular quantum number, magnetic quantum number, right? So, आपके पास इसी तरह यहाँ पे for the case of nucleus, you are going to see the term nuclear spin quantum number represented by capital I. Okay, and as it is already mentioned over here that magnetic nucleus, जिसकी I value जो होगी 0 के बराबर नहीं होगी, they are always going to behave as a tiny bar magnet. Now, अगर आपसे यही पूछ लिया जाए कि how you are going to say that a magnetic nuclei can behave as a tiny bar magnet, and why you are calling it a magnetic nuclei? So the answer lies in this particular fact that why nuclei behave as a tiny bar magnet, because they contain protons as well as neutron. You know कि एक nucleus के बीच में आपके पास proton, that is positively charged particle, and neutral charge, that is neutron, is present, right? Now, these two both of them have magnetic properties, and that particular property is itself known as spin, right? Which is why nuclei consistently spin around its own axis. नाउ दिस स्पिन क्रिएट्स अ मैग्नेटिक मोमेंट. अब आप इसे बहुत सिंपली समझ सकते हो, जैसे आपके अर्थ है, अर्थ रोटेट करती है सन के अराउंड, राइट? दिस इज योर सन, राइट? अर्थ इज कंसिस्टेंटली रोटेटिंग अराउंड द सन, बट जब ये रोटेशन आपकी अर्थ कर रही है सन के अराउंड, इट इज ऑल्सो रोटेटिंग अराउंड इट्स ओन एक्सिस, या अपने एक्सिस के अराउंड भी रोटेट कर रहा है, ठीक है? और जब ऐसा होता है तो देयरफॉर इट क्रिएट्स और इट जनरेट्स सेकेंडरी मैग्नेटिक फील्ड, जिसे ये कह सकते हैं आपके पास इंड्यूस्ड मैग्नेटिक फील्ड. सो जस्ट लाइक दैट आपका जो न्यूक्लियाई है, व्हेन इट्स स्पिनिंग अराउंड इट्स ओन एक्सिस, इट विल देयरफॉर क्रिएट अ मैग्नेटिक मोमेंट व्हिच इज क्वाइट सिमिलर टू द मैग्नेटिक मोमेंट क्रिएटेड बाय स्मॉल बार मैग्नेट. And this is the reason why your nuclei can behave as a tiny bar magnet, right? So the magnetic moment of individual nucleon that is proton and neutron is very small, but the sum total of the magnetic moments of all the nucleons, spin property of proton and neutron, this create a tiny magnetic field, and therefore it behaves like a small bar magnet. So I hope this particular reason, and if someone asks you that why magnetic nuclei can behave as a tiny bar magnet, so the reason lies in this particular slide, right? So when a group of protons and neutrons, they are arranged in a particular way in a nucleus, the net magnetic field created by these tiny bar magnet adds up to produce quite stronger magnetic field. Now this is why nuclei behave as a tiny bar magnet with magnetic moments that can be further measured, and these such kind of nuclei, they itself has quite great scientific applications such as MRI, आपकी जो magnetic resonance imaging है वहाँ पे use हो सकते हैं, then आपका definitely NMR में use हो सकता है, which is why this is the physical basis of NMR spectroscopy, correct? So this is the reason that we have used this particular term over here. Now going back to the previous slide once again, right? So that is what we are saying, that the magnetic nucleus which behave as a tiny bar magnet can be represented as this. The circle is representing the nuclei, and this particular symbol, the arrow, it indicates the south to north polarity. That means the direction of magnetic field is from south to north. Okay, and the circle, as I told you, it represents the nucleus. So your nuclear spin quantum numbers, it can have either 0 value, either 1 or either 1.5. So we are going to see over here these three cases. Alright, so these are those cases. Now, as I've told you that it can either have 0 value, it can either have 1, 2, 3 value, then, or it can have the fractional plus half or 3 by 2, 5 by 2, 7 by 2 value. Okay. So when such kind of thing, and when you are going to get this value of your nuclear spin quantum number, that is what you are going to see. Okay, let me correct this over here. The value of nuclear spin quantum number, that is I, not N. Okay, and if the mass number is odd, that is 1, 3, 5, 7, 9, and atomic number either could be odd or even, in that case you are going to have the value of nuclear spin quantum number in fraction, that is plus half, 3 by 2, 5 by 2. बच्चे आपको ये याद करना पड़ेगा. So we have examples that जहाँ पे आपका nuclear spin quantum number की value half है, वो है आपके पास H1, then your carbon 13 isotope, N15 isotope, F19 isotope. जहाँ पे I की value 3 by 2 है, that is boron 11, sodium 23, chlorine 35, bromine both 79 and 81 isotope. Then third is the case जहाँ 5 by 2 value है, वो आपके पास एक एग्जाम्पल है O17 isotope का. ठीक है, अब ये आपके पास केस आ गए. तो आप देखो यहाँ पे H1 का ही केस ले लो, तो यहाँ पे आपका एटॉमिक नंबर जो है that is also 1 and mass number is also 1. ठीक है, दूसरा कोई केस ले लेते हैं जहाँ पे आपका एटॉमिक नंबर इवन हो, ये ले लो C13. यहाँ पे आपका एटॉमिक नंबर इज इवन बट मास नंबर इज ऑड. सो अगर आपका मास नंबर ऑड है, फिर चाहे आपका एटॉमिक नंबर इवन हो या ऑड हो, वहां पे फ्रैक्शनल वैल्यू आएगी क्वांटम न्यूक्लियर स्पिन क्वांटम नंबर की. एंड अगर दोनों ही आपके इवन है, वैल्यू इज गोइंग टू बी 0, एंड दैट इज इजी टू आइडेंटिफाई. दैट इज द केस ऑफ हीलियम, कार्बन एंड ऑक्सीजन. इफ mass number is even and atomic number is odd, that is the case of value 1 and 3. where I is your 1 and 3, and that is the case of this particular examples. So I की value यहाँ पे 1 है for N14 and deuterium. So since an atomic number is associated with charge, therefore, like any other rotating charge, it generates its own magnetic field along the axis of the spin. So ये चीज तो मैं आपको पहले ही अभी explain कर चुकी हूँ that how therefore the magnetic nuclei behave as a tiny bar magnet, right? So therefore such a nuclei, they behave as a bar magnet and has characteristic magnetic moment represented by mu, correct? So proceeding further in the following topic, so when molecule with I value greater than 0, that could be I is equal to 1, 2, 3 and so on, when such kind of molecule with this value of I is placed in external magnetic field, it is found to have a set of discrete orientations with respect to the applied magnetic field. So these various orientations are referred to as spin states. अब देखो बच्चा, इसके कहने का मतलब क्या है कि ये जो आपका न्यूक्लियर है, स्पिनिंग न्यूक्लियर, एज ऑफ नाउ इट इज प्रेजेंट इन नो फील्ड, मतलब आपने कोई बाहर से एक्सटर्नल मैग्नेटिक फील्ड प्रोवाइड नहीं की. अब जब आपने एक्सटर्नल मैग्नेटिक फील्ड फ्रॉम साउथ टू नॉर्थ इस पोलैरिटी में आपने इंड्यूस करवा दी, तो क्या होगा, there comes a set of discrete orientations. Discrete orientations का मतलब क्या है with respect to your external magnetic field, कि अगर आपकी external magnetic field की डायरेक्शन आपके पास यहाँ पे, just give me a second, या ये है साउथ टू नॉर्थ, तो एक ओरिएंटेशन क्या हो सकती है आपके स्पिनिंग न्यूक्लियर की, या तो वो इसी डायरेक्शन में पैरेलल ही चलेगा एक्सटर्नल मैग्नेटिक फील्ड के, या फिर इसके एंटी पैरेलल चलेगा. सो अगर आपके पास पैरेलल डायरेक्शन में मूव करता है with respect to the external magnetic field, the precessing nuclei will go to the lower energy state. That particular precessing nuclei which is orienting itself with respect to the external magnetic field parallelly, and if it is anti-parallel, that will go to the higher energy state. So you can see it is quite mentioned over here that a nucleus with spin at lower energy generates a magnetic field in the direction of external magnetic field, that is parallel आपके पास चल रहा है वो, and अगर anti-parallel वाला केस होगा तो ये आपके पास ये वाला होगा. So the spin with higher a nucleus with spin at higher energy that generates magnetic field in opposite direction to the external magnetic field. तो अगर ये आपकी external magnetic field की डायरेक्शन है तो इस वाले स्पिन की ये डायरेक्शन होगी. अंडरस्टूड? सो ये आपको, ये बेस है इस चैप्टर का, ये आपको यहीं पे क्लियर हो जाना चाहिए, राइट? सो फॉर न्यूक्लियाई विद स्पिन क्वांटम नंबर I is equal to 0, I is greater than 0, there are 2I plus 1 allowed spin state. So over here you can see the spinning top. This is how it looks like, and you might have used in your childhood days as well. So we are going to compare the spinning top with that of the spinning nuclei. So that is what we are going to see, that how just like that of spinning top, your spinning nuclei creates its own magnetic field by revolving around its own axis and thereby generating its own secondary or induced magnetic field. Okay, so when the spinning top is disturbed a little, its spinning axis will trace out circle perpendicular to the Earth's gravitational field, and such a motion is known as precession. So over here you can see a case of spinning proton, and this is the case of your spinning nuclei. So what is happening, just like the spinning top, your spinning nuclei is revolving around its own axis like this in this particular direction, and they will trace out a circle perpendicular to the direction of this Earth's gravitational field, and therefore this motion is said to be known as precession. और जो इसी की वजह से आपके पास फ्रीक्वेंसी जनरेट होगी उसको आप बोलोगे प्रिसेशनल फ्रीक्वेंसी, वो हम पढ़ेंगे आगे, ठीक है? So in the same way, hydrogen atom spinning in an applied magnetic field will experience a torque. What is that? That is a force. It's perpendicular to the axis of nuclear magnetic, which will tend to align it with the field. So since the nuclear magnet is spinning right now, it will not align with the external magnetic field, but instead of aligning with the external magnetic field, ये क्या करेगा, precess करेगा around it like this, जैसे spinning top की तरह. उसी तरह ये आपका magnetic nuclei भी precess करना शुरू कर देगा around the your external magnetic field with a certain angular frequency, that is omega, जिसको आप बोलोगे प्रिसेशनल फ्रीक्वेंसी, और जिसका एक और नाम यूज होता है लार्मर फ्रीक्वेंसी। तो आई होप आपको ये चीज समझ आ गई होगी कि कैसे स्पिनिंग टॉप से हमने कंपेयर किया है यहाँ पे आपके प्रोसेसिंग न्यूक्लियाई को। ठीक है, सो फ्रीक्वेंसी एट विच ए प्रोटॉन प्रोसेस वो डिपेंड करता है कि कितनी स्ट्रेंथ के अप्लाइड मैग्नेटिक फील्ड है आपकी, इधर अप्लाइड मैग्नेटिक फील्ड स्ट्रेंथ वो कितनी है आपके पास, उस पर रिलाई करेगा आपकी फ्रीक्वेंसी ऑफ प्रोसेसिंग प्रोटॉन। अंडरस्टूड? So the stronger is the applied field, higher is the precessional frequency. And for a proton, अगर आपके पास applied field की value है 14,100 gauss. Gauss is one of the unit of your magnetic field, and we also use one another unit, that is Tesla. So the frequency, the precession frequency in this particular magnetic field, remember that always, that is going to be 60 megahertz. That is 60 million cycles per second. तो अगर आपका प्रोटॉन जिसकी अप्लाइड मैग्नेटिक फील्ड की वैल्यू है 14,100 गॉस, उस केस में उसकी प्रिसेशनल फ्रीक्वेंसी की वैल्यू हो जाएगी 60 मेगाहर्ट्ज। एंड आपको पता है कि आपको जो प्रोटॉन है, अभी हमने देखा दैट इट हैज टू अलाउड स्पिन स्टेट प्लस हाफ एंड माइनस हाफ, तो वो प्रोसेस करेगा दो प्रिंसिपल ओरिएंटेशन से, वन विद द अप्लाइड मैग्नेटिक फील्ड एंड हैविंग लो एनर्जी, एंड वन अपोजिंग टू द अप्लाइड फील्ड हैविंग हायर एनर्जी. So when the precessional frequency of nucleus proton is exactly equal to the frequency of electromagnetic radiations, the absorption will occur and the nuclei in no state flip to the high energy spin state. When this occurs, the nuclei and the radio frequency beam are said to be in resonance, and this resonance is due to the magnetic property of nuclei, जिसे आप बोलते हो न्यूक्लियर मैग्नेटिक रेजोनेंस, एंड देयरफॉर एनएमआर. तो बेटा यहाँ पे आपकी जो फ्लिप वर्ड यूज हुआ है, इसके लिए भी आपके पास इंस्टेड ऑफ डायरेक्टली आस्किंग द प्रिंसिपल ऑफ एनएमआर, दे विल आस्क यू व्हाट इज स्पिन फ्लिपिंग. तो आपको यही प्रिंसिपल ऑफ एनएमआर एक्सप्लेन करना है उसने, ये सारा जैसे यहाँ पे एक्सप्लेन किया है. So yeah, such kind of question can be asked in the paper as well. So I hope this is quite clear to you. और हमने ये जो इसकी प्रिंसिपल ऑफ एनएमआर की बात अभी यहाँ पे की है, ये हम ऑलरेडी पीछे डिस्कस कर चुके हैं स्टार्टिंग में. So I hope this is quite clear to you, and in case you face any difficulty, you can ask me in the comment section below. So the exact amount of radio frequency energy needed is depending upon the strength of external magnetic field, that is represented by H naught, and the particular equation is given like this: delta A is equal to H nu, that is further is equal to H by 2 pi H naught, like that. Okay, so over here this particular gamma is signifying gyromagnetic ratio. Okay, then H is your Planck's constant, H naught is signifying your strength of external magnetic field, right? And therefore what is gyromagnetic ratio? अगर आपसे पूछ सकते हैं ये क्या होता है, पता होना चाहिए, एग्जामिनर की मर्जी है, वो कुछ भी पूछ सकता है 1 मार्क्स में, 2 मार्क्स में. So gyromagnetic ratio is the ratio of magnetic moment to the angular moment and is constant for each nucleus. In case of proton, the value is going to be 26750. So हम पढ़ ही proton NMR रहे हैं, तो definitely you should remember the value of gamma in this case. Okay. Now it may be noted that from here that an NMR instrument with magnetic field strength of 1.41 Tesla, और इसी को आप लिख सकते हैं in terms of Gauss 14100 Gauss, are operating at a constant radio frequency of 60 megahertz. तो मैंने आपको भी पीछे बता दिया था कि जो प्रोटोन है जिसकी मैग्नेटिक फील्ड स्ट्रेंथ की वैल्यू इतनी आएगी, वो 60 मेगाहर्ट्ज पे आपके पास प्रोसेस कर रहा है. ठीक है, एंड इट कैन इंड्यूस ट्रांजिशंस ओनली in the proton spin state in a molecule and is not useful for the other nuclei. मतलब कहने का मतलब क्या है कि एक पर्टिकुलर मॉलिक्यूल में जो ट्रांजिशन हो रही होंगी वो क्या किसमें हो रही होंगी, प्रोटॉन में ही हो रही होंगी, प्रोटॉन के न्यूक्लियाई में ही हो रही होगी, कार्बन के न्यूक्लियाई की बात नहीं करेगा वो वहां पे, since we are talking about proton NMR only, right? So therefore separate instruments are required for observing transition in such elements like carbon, phosphorus, fluorine. तो उसके लिए separate instrument आते हैं आपके पास. Now next is what we are going to see, the population densities of nuclear spin states. First of all, we are going to discuss the excess population in the nuclei. So the difference between the number of nuclear population density in these two spin states is called population difference or excess population. तो आपके पास न्यूक्लियर पॉपुलेशन डेंसिटीज की जो दो स्पिन स्टेट्स आती हैं लोअर एंड एक्साइटेड स्पिन स्टेट में, उसमें आपके कितने न्यूक्लियाई नीचे वाले स्टेट में है और कितने ऊपर, उसका जो डिफरेंस है दैट इज व्हाट वी कॉल पॉपुलेशन डिफरेंस और एक्सेस पॉपुलेशन जिसे बोलते हैं. So this is very much lower as compared to the two different spin state population densities. So you can see in this diagram that this is the lower level that is having this orientation and this is the upper level, this is having this orientation. So let's just say, and always you need to remember that the lower spin state is going to have the higher number. Why is it so? Because आपको पता है कि आपका जितने भी जो भी कंपाउंड है वो as such initially तो ग्राउंड स्टेट में प्रेजेंट होते हैं, ठीक है, और ग्राउंड स्टेट में सभी के सभी न्यूक्लियर तो आपके जो है वो एक्साइट नहीं हो जाएंगे, वही वाले होंगे. जब अगर आप प्रोटॉन की बात करें तो सिर्फ प्रोटॉन्स वाले न्यूक्लियर होंगे, बाकी तो पीछे रह जाएंगे न्यूक्लियर कार्बन के या फिर कोई और अगर उसके साथ क्लोरीन लगा है तो, ठीक है. So that is what we are trying to say over here is that lower level will be always consisting excess population, right? Now let's just say that your lower level is having n plus 9 excess population. So n, let's just say the value of n is this, okay, and this particular lower state is going to have 1 000 009 in the lower state, and in excited state it has 1 000 So that means in as compared to the lower spin state, the nuclei over here is having 9 excess population in case of protons, that is H1, right? This is what we are going to see. And how you calculate excess population? By using the formula n upper by n lower. तो यहाँ पे आपके पास n upper by n lower ये कैलकुलेट करके आपके पास ये आ गया, और वो आपने कैसे किया वो मैंने आपको अभी यहाँ पे समझा दिया. हमने एग्जांपल लिया कि मान लो n की वैल्यू आपके पास इतनी है और ग्राउंड स्टेट में डेफिनेटली आपके पास 9 यहाँ पे एक्सेस न्यूक्लियर है, और ये याद रखना है आपको कि while talking about the proton there is always going to be 9 excess nuclei in the lower spin state. Okay, so that is one thing over here. Okay, and this means that population difference on excess population is 9. In total approximate 2 million nuclei. मतलब अगर आप अपर और लोअर न्यूक्लियर का टोटल कर लो that is approximately 2 million nuclei, right? तो उनमें से आपके पास एक्सेस न्यूक्लियर कितने थे? उसमें आपके पास 9 एक्सेस न्यूक्लियर थे लोअर स्टेट में, ठीक है. So the excess nuclei are allowed for or absorbing nuclear resonance. These excess nuclei are the reason only जिसकी वजह से आपके पास रेजोनेंस देखने को मिलेगी यहाँ पे, ठीक है. एंड therefore जब आपके पास 60 मेगाहर्ट्ज का इंस्ट्रूमेंट आप यूज कर रहे हो, उस केस में आपके पास क्या होगा? When 60 megahertz instrument is used, applied field radiation is applied, the transition occurs upward and also the stimulated transition downward. That means कि अगर आपके पास transition absorption करने के बाद ऊपर जाके इस तरीके से आ रहा है तो there are chances emission के बाद ये वापस उसी state में return हो जाए. So if that situation occurs, that is the case of saturation, and you have to avoid this condition if you want to get your NMR spectra, right? So the population of nuclear spin state and lower spin state become exactly equal in this case, and therefore we absorb no net signal, and this situation is saturation. So saturation occurs in NMR when NMR radio frequency signal is way too higher. So you have to carefully take it into consideration while you are going to take the NMR spectra of any compound, कि आपको अवॉइड करना है कि आपके सैंपल की सैचुरेशन ना हो जाए, कि आपका एक्साइटेड स्टेट में जो आपका न्यूक्लियर गया वो ऐसे वापस उसी टाइम पे ना आ जाए. तो क्या होगा? अल्टीमेटली सैचुरेशन हो जाएगी एंड इसकी वजह से आपके पास कोई सिग्नल ऑब्टेन नहीं होगा, राइट? So this is one thing over here. And if the energy difference between the two spin states of proton, that is any proton, that is this and this, the energy difference between it is at 60 megahertz is 2.39 into 10 raised to the power minus 5 kilojoule per mole. अगर आपके पास इतनी एनर्जी, जो कि इतनी वैल्यू आएगी आपके पास प्रोटॉन के केस में at 60 megahertz इंस्ट्रूमेंट, एंड उस केस में क्या होगा? सिंस दिस एनर्जी डिफरेंस इज वे टू स्मॉल, देन योर थर्मल एनर्जी ड्यू टू रूम टेम्परेचर, जो आपका रूम टेम्परेचर है उसकी वजह से जो थर्मल एनर्जी अवेलेबल होगी हमारे पास, that is only sufficient enough to populate both the spin states. Right? Correct. So this is however a slight excess of nuclei in the low energy spin state. So the magnitude of this energy difference, we can calculate it by using the Boltzmann distribution equation that is present over here. That is number of nuclei in the upper spin state divided by number of nuclei in the low spin state is equal to e raised to the power delta E, that is change in energy, divided by kT, that is K stands for gas constant, value is given over here, and T stands for absolute temperature. So using this value you can calculate the magnitude of the energy difference, right? Now this is the diagram related to the excess excess population, and over here you can see that as discussed in the previous slide, we have already said that room temperature, the thermal energy provided from the room temperature is sufficient enough to populate the spin states, right? So you can see that there are total of 9 nuclei present in the lower spin state, and only 7 of them are excited on the higher spin state. So which means that there are 2 excess nuclei present in the ground state, right? So this is how you can say that there are 2 excess nuclei in this particular case, and you can see that the excitation occur like this, and they have just shown that how excitation and relaxation occurs. So excitation occurs when the transition occurs between the low state and the excited state on absorption of energy, then that is this case, and relaxation occurs when the absorbed energy is released or emitted as such, and therefore the excited nuclei has returned to its ground position, and that process is known as relaxation. So we are going to take up next topic, that is relaxation processes only, and the various kind of radiation-less transition by which a nuclei is in upper spin state can return to the low spin state by emission of absorbed energy is called relaxation process. Simple सी बात है, absorbed energy को जब आपके excited nuclei ने emit कर दिया तो आपके पास जो है, और वो भी आपकी radiation less emission होगी, ठीक है? तो which is why it is radiation less transition, and उस केस को आप बोलोगे relaxation. और जो processes हम देखेंगे यहाँ पे, that would be relaxation processes. First one is spin-spin, second one is spin-lattice. Spin-spin also known as transverse, and spin-lattice is known as longitudinal. So in the case of spin-spin relaxation, which is also known as transverse relaxation, that involves the mutual exchange of spins. क्या मतलब है कि अगर आपके पास 2 processing nuclei जिनकी energy मान लो almost बराबर की है, and the magnetic vector component of these processing nuclei is similar, that is mu is similar to that of the induced transition. Okay, if it is, the magnetic vector is equal to the induced transition in the neighboring nucleus, then what will happen? The transfer of energy takes place, which means कि ये वाला जो spin है वो अपनी energy transfer कर देगा इस spin को, and therefore उसकी orientation को change कर देगा like this, and इसकी खुद की orientation भी इसके respect में change हो जाएगी like this. So first one which was planar, which was parallel to the applied magnetic field will now become anti-parallel, and then second one will become parallel. So this is how the mutual exchange of energy is occurring. The mutual exchange of spin energy is occurring over here, which is why the term spin-spin relaxation is used for this particular case. So it involves a mutual exchange of spin by 2 processing nuclei, as you have seen, in the close proximity to each other, when their magnetic vector component is same as it is required to induce transition in its neighboring nucleus. मतलब क्या है यहाँ पे कि दोनों का magnetic vector component अगर same है, ठीक है, to induce transition, then in that case आपका mutual exchange of spin energy हो जाएगा, और उसको आप बोलोगे spin-spin relaxation. Simple, right? So this is how you are going to define it, and in this process जब आपका एक न्यूक्लियस एनर्जी लूज करता है तो दूसरा गेन कर रहा है, तो कोई देयर इज नॉन नेट लॉस ऑफ एनर्जी, कोई टोटल लॉस नहीं हो रहा है एनर्जी का यहाँ पे. अगर यहाँ ये वाला न्यूक्लियर आपका एनर्जी लॉस कर रहा है तो इसकी एनर्जी इसने गेन कर ली, और जब इसने एनर्जी लूज की तो इसकी एनर्जी इसने गेन कर ली, therefore changing its orientation like this, right? So therefore this process shortens the lifetime of individual nucleus in higher spin state, but does not contribute to the maintenance of required excess of nuclei in the low spin state. कि क्या बोला है इन्होंने यहाँ पे, excited nuclei की जो spin state है, जो उसकी लाइफ टाइम है उसको उसकी शॉर्ट कर देगा एंड इट देयरफॉर डज नॉट कंट्रीब्यूट एट ऑल टू द मेंटेनेंस ऑफ एक्सेस ऑफ द न्यूक्लियाई इन लो स्पिन स्टेट. दैट इज वन थिंग इन दिस केस. Correct. So proceeding further to the spin lattice relaxation. Now in this case, it involves the transfer of energy, definitely like in the previous case, from the nucleus in its high energy state to molecular lattice. अब उसमें क्या होता था कि दो न्यूक्लियाई के बीच में आपकी ट्रांसफर ऑफ एनर्जी हो रहा था. यहाँ पे एक न्यूक्लियस से कंप्लीट मॉलिक्यूलर लेटिस में आपकी ट्रांसफर ऑफ एनर्जी आपको देखने को मिलेगी. करेक्ट. सो lattice implies the entire framework of aggregate of neighbor. यानी कि आपका अगर मान लो ये आपका मॉलिक्यूल है CH3CH2, तो सिंपल सी बात है, जब आपके मिथाइल के तीनों प्रोटॉन्स में आपस में म्यूचुअल एक्सचेंज ऑफ एनर्जी हो रहा होगा तो उसे आप बोलोगे स्पिन स्पिन. एंड वही अगर मान लो कि इसके जो एक पूरे मिथाइल का जो आपकी एनर्जी है वो आपके उसके नेबरिंग प्रोटॉन यानी कि CH2 के मिथाइलिन प्रोटॉन्स के उसमें उसकी एनर्जी ट्रांसफर हो रही है. सो दैट इज गोइंग टू बी द केस ऑफ स्पिन लेटिस. दिस इज हाउ यू कैन अंडरस्टैंड. सो लेटिस इंप्लाइज द एंटायर फ्रेमवर्क ऑफ एन एग्रीगेट ऑफ नेबर. एग्जाम्पल सैंपल सॉल्वेंट. एक सैंपल आपका जिस सॉल्वेंट की प्रेजेंस में आपने लिया है उसकी सॉल्वेंट के फ्रेमवर्क पे सैंपल का जो है एनर्जी ट्रांसफर हो सकती है सॉल्वेंट में. ठीक है. दैट इज व्हाट दे आर ट्राइंग टू इम्प्लाई. सो द मॉलिक्यूलर लेटिस कंटेन प्रोसेसिंग न्यूक्लियाई all of which are undergoing translational, rotational, vibrational motions. So hence a variety of magnetic field is present in the lattice. So that is one thing. सिंपल सी चीजें आपको याद रखनी है. स्पिन में आपकी स्पिन दो न्यूक्लियर स्पिन्स के बीच में एनर्जी ट्रांसफर हो रहा था और यहाँ पे आपका ये एक न्यूक्लियाई से या एक पूरे मॉलिक्यूल के एक पर्टिकुलर प्रोटॉन के न्यूक्लियाई से दूसरे लेटिस के उसमें एनर्जी ट्रांसफर हो रही है. दैट इज व्हाट दे आर सेइंग. दैट्स इट. सो द एनर्जी इन दिस प्रोसेस इज ट्रांसफर टू द कंपोनेंट ऑफ लेटिस. कैसे एनर्जी ट्रांसफर हो रही है यहाँ पे? एज एडिशनल ट्रांसलेशनल, रोटेशनल एंड वाइब्रेशनल एनर्जी. सो द टोटल एनर्जी remains same but transfer energy is ultimately converted to thermal energy because you require thermal energy for the excitation, right? So the nuclei returns to the low energy spin state without nucleus being even promoted to high energy state. तो मतलब आपका जो low energy spin state था वहां से आपको सीधे molecular lattice में चला गया और वहीं से वापस low energy spin state में चला गया. higher excited energy spin state की तो यहाँ पे कोई बात ही नहीं हुई है. समझ आई बात? ठीक है. So the nucleus returns to the low energy spin state without nuclei being promoted to high energy spin state. So the relaxation process maintain excess of nuclei in the low energy spin state. Now see, पिछले केस में आपने देखा था कि लो एनर्जी स्पिन स्टेट में एक्सेस न्यूक्लियाई को मेंटेन करने का काम स्पिन रिलैक्सेशन नहीं करती. बट यही यहाँ पे पॉइंट ऑफ डिफरेंस आ गया कि इन दिस केस दिस प्रोसेस मेंटेन्स द एक्सेस ऑफ न्यूक्लियाई इन द लो एनर्जी स्टेट. ओके. एंड विच इज क्वाइट नेसेसरी कंडीशन बिकॉज मैंने आपको पहले ही बताया था कि अगर आपको NMR का फिनोमेना ऑब्जर्व करना है, NMR स्पेक्ट्रा अगर आपको चाहिए तो देयर शुड बी एक्सेस ऑफ न्यूक्लियाई प्रेजेंट इन द लो एनर्जी स्पिन स्टेट. And spin lattice phenomena is usually observed in solid. So this is all about this particular topic. And one more thing you need to keep in mind that broad resonance signals are the one that normally observed for solid and viscous liquids. Because in such cases usually spin relaxation time is very short. So broad signals like something like this. Like you know, it would not be like this, it will be something like this. Broad signals. And okay, that is one thing. And for long lived excited states, sharp resonance signals like this, sharp resonance signals are observed. So these are the broad ones, these are the sharp ones. This is how you see such kind of signals are going to be noticed in the upcoming NMR spectra when you will be able to read them. आप ये चीजें अच्छे से समझ जाओगे, right? So that's all about it. So I hope आज जितने भी टॉपिक हमने कवर किए हैं, इंट्रोडक्टरी पोर्शन, न्यूक्लियर स्पिन स्टेट, योर एक्सेस population, then principle of NMR, I hope relaxation processes, I hope they all are quite understandable to you. And अगर ऐसी कोई चीज है जो आपको समझ नहीं आई है, you are more than welcome to ask that in the comment section below. And if you like this channel, do press the bell icon for more updates. Like, subscribe, share and keep supporting. Thank you so much.